All right, so in the last video we saw something about where this equation comes from and what it means. Let's see what the implications of this equation are. First of all, we have this theorem that says if M, which is a matrix, and in all of these examples we are thinking of M as a square matrix. You can't have a non-square matrix have a determinant. Why is that? Because the column index is a permutation of the row index, and so that means there must be the same number of columns as there are rows, because the column numbers are simply rearrangement of the row numbers. So rows equals columns, so M must be square. All right? So if M has a row consisting entirely of zeros, then Mi sigma I equals 0 for every sigma and some I. Moreover, the determinant of M is equal to 0. All right, so let's think about that, what he's saying here. What we're saying is that think of the row I. Let's think, for example, of the row 5. Suppose the row 5 is entirely 0. That means that M5J is always 0, no matter what J is. Now, this determinant has a term in it that says M5 sigma of 5. So no matter what sigma of 5 is, M5 sigma of 5 is going to be 0. That means that every term in this sum is 0, so the determinant is 0. So if we have a row of zeros, the determinant is 0. Now this section makes the point that determinants have an awful lot of terms. There's one term here for every permutation, and we mentioned that the number of permutations is n factorial. So for 4, for instance, that's 4 times 3 times 2 times 1, or 24, and then it goes rapidly up from there. From 5 it's 120, and it gets very, very big quickly. Now let's look at some special cases. For example, suppose M is a diagonal matrix. Then what do these terms say? Well, look at this expression here. If M is a diagonal matrix, then Mij is 0 whenever I is unequal to j. In other words, if I have any term that has the row index unequal to the column index, I'll get a 0. Because I'm taking a product, even if even one of these has row index unequal to column index, then the term is going to be 0. So the only term out of all these terms is the term in which I have the same row and same column, so this would have to be M11, M22, all the way down to MNN. Okay? That's what we call the trivial permutation or identity permutation, and that takes 0 row swaps. The sign of that is 1. So the result is simply the product of the diagonal entries. So the determinant of a diagonal matrix is the product of its entries, of its non-zero entries. Of course, the identity matrix is a special case of that, so the determinant of the identity matrix is 1. Okay. Now, let's see if we can apply determinant to the inverse of a matrix. Remember how we computed inverse of a matrix. So let's look at the issue here. I summarize it over here. We compute the inverse of a matrix by performing row operations on the augmented matrix formed by M and the identity matrix. And you do that until you get the identity matrix on the left and M inverse on the right. So that means that the identity matrix is related to M inverse by row operations. Right? Now we happen to know that the determinant of the identity matrix is 1. So if we can discover what row operations do to the determinant, we can relate the determinant to M inverse. So the process of finding M inverse can be related to something to do with determinant if we can see what the relation is between row operations and determinant. So that's what the strategy is going to be. Let's go back and follow up on that. Well, first of all, suppose you swap rows I and j. Okay? So what you're actually doing here is you're making a swap. Now we already saw that a swap corresponds to a sign change in the permutation. Right? If I do a permutation, then do one more swap, then that's going to change the sign of a permutation, because it's going to change an even permutation to an odd permutation, and vice versa. Okay, one more swap is going to change from even to odd or from odd to even. So the upshot is that that's going to change the sign of the entire determinant, because it's going to change the sign of every term in the sum that gives you the determinant. All right? So that's summarized here. If m and m prime differ by a row swap, then the determinant of m prime is negative the determinant of m. Okay? Now remember that row swap corresponds to an elementary matrix, and the notation was EIJ, which means that I swap rows I and row j. Okay? All right. Now amazingly, this gives us a neat fact that's for free. Suppose I have a matrix that has two rows the same. Okay? Think about that. Matrix, two rows the same. If I swap those two rows, then I haven't changed the matrix. But according to this argument, I've changed the sign of the determinant. Okay? So on the one hand, the determinant can't have changed because it's the same matrix. On the other hand, since I've swapped two rows, the sign has changed. So the only way that the two determinants can be equal and have opposite signs is if they're both 0. So in fact, if m has two identical rows, then the determinant of m is 0. So that's a fact that we almost get for free based on what we've talked about. All right, so row swap is just one kind of elementary matrix. Let's look at row swap a little bit more and then go on to the other elementary matrices. All right, now, what does row swap matrix actually look like? Well, row swap matrix, to accomplish the row swap on a matrix, one way of thinking about that is you accomplish the same row swap on the identity and then multiply by the matrix in question. Okay, here we're writing the matrix M as its rows, and M prime is the rows switched. Now, to get the rows switched, I multiply the original matrix with row I and row j. I multiply that on the left by the identity, which has the two rows switched. All right, this matrix here is the identity matrix, except this one gets knocked out and put down here. This one gets knocked out and put up here. Okay? So the elementary matrix corresponding to row swap looks like this. Now, what about the determinant of this matrix? Okay. Well, this matrix is just the identity with two rows swapped. We know that swapping rows changes the sign of the determinant. So the determinant of this matrix is -1. All right. So in fact, look at what we have here. By swapping, one way to swap the two rows of a matrix is by multiplying by this row swap matrix, EIJ, which is just this matrix here. Now we know that the determinant of M prime is negative the determinant of M, because the rows have been swapped. On the other hand, we know that the determinant of this row swapped identity is also -1. So that means the determinant of M prime is -1 times the determinant of M, and -1 is the determinant of EIJ, so we can write the determinant of the row swapped matrix is determinant of the identity row swapped times the determinant of the original matrix. And that's a pretty cool equation. It's kind of break apart the determinant of a compound matrix into the determinants of its component parts. And we're going to see, not to spill the beans, that this holds for every elementary matrix. The same thing holds for row multiplication and row multiply and add. Well, let's go ahead and see that. To do a row multiplication, we can take the same strategy. To do row multiplication on a matrix, we're writing the rows like this, we can multiply it on the left by this elementary matrix, which is the same row multiplication accomplished on the identity matrix. Okay? So if I want to multiply the jth row here by lambda, the way to do that is multiply the jth row of the identity matrix by lambda, and then multiply M on the left by this matrix. Okay? Well, that's how I get my new matrix, which is the original matrix with the jth row or the ith row rather, multiplied by lambda. All right, now, what's the determinant of this elementary matrix? Well, this matrix is a diagonal matrix. These are all zeros off the diagonal. And we saw previously that the determinant of a diagonal matrix is the product of the diagonal entries. What's the product of the diagonal entries? Well, they're all 1 except for this lambda. So the product is going to be 1 times 1 times 1 times 1 times lambda times 1 times 1. So the product is lambda. Okay? So the determinant of this row swap matrix is lambda. Right now, what does multiplication by lambda do to the determinant of the matrix M? Okay? What I've done is I've taken M, I've multiplied the ith row by lambda. How does that change the determinant? Okay? Well, if I look at the determinant of M prime, the only difference between M prime and M is that in the ith term here in this product, I'm going to replace the mi sigma I with lambda mi sigma I. That's the only change. And every term in the product will be changed the same. The upshot is the entire sum gets multiplied by lambda because each term in the sum is multiplied by lambda. So I pull the lambda out front and I get the determinant of the matrix M with row I multiplied by lambda is lambda times the determinant of the original matrix. Multiplying one row of a matrix by a constant will multiply the determinant by that same constant. Now be careful, if you multiply the entire matrix by a constant, the rule is different. But if I multiply one row of a matrix by a constant, then the determinant is also multiplied by the same constant. And that lambda, what is that lambda? Well, that lambda was the same as the determinant of this elementary matrix. Okay? This elementary matrix is denoted by Ri of lambda. So again, we have this formula that the determinant of the product, Rim, is the determinant of the row operation matrix times the determinant of the original matrix. Okay. Now, there's just one more type of elementary operation, which is row multiply and add. So it's expressed here as mu times Rj plus Ri. So I'm adding mu times row j to row I. All right? And the way that matrix is written is Sij mu. Okay, so the mu denotes the constant that the rows being multiplied by. And the way to get the elementary matrix is perform the same operation on the identity matrix. So this identity matrix was obtained by taking this row here, which would be the jth row, multiplying by u and adding it to row I. And this is the ith row here. Okay, so this matrix looks like a full identity matrix with ones everywhere in the diagonal, plus the singleton mu off in the boonies here. Okay, every other entry is 0. These are all zeros. So this mu is washed in a sea of zeros. All right. Now you can check that if you multiply this matrix times any matrix, that will give you in the ith row, it will give you the ith row plus mu times the jth row. You can think about that. If I multiply this row here by the columns here, I'm always going to pick up from this the ith row, and here I'm going to pick up mu times the j row entry. So I'm going to actually get this. Right? So how does this affect the determinant? Well, all of the terms in the product are the same except for this one. The only change is in the ith place in this product, where I have the mi sigma I, but I've added this mu mj sigma I. The sigma I is the same because you're adding the entries in the same column. The rows are different, the I and j are different, but the columns are the same. Okay. Now, since this is only one term where I'm adding, I can use distributive law. All of these other constants multiply this one, and they all multiply this one, so I can break it apart into two parts. It's easiest to see if you take this sum term and move it to the end, and then you have some long number times a sum of two numbers. I can break each term here up into two terms, and that means I can break the entire sum up into two sums. And what do I have? Well, lo and behold, each one of these is a determinant. This is the determinant of my original matrix. This is the determinant of a matrix that has the jth row multiplied by mu and replacing the ith row. The jth row is replacing the ith row. Now I can pull out the mu, and that means the ith row here is equal to the jth row there. Now what do we know about a matrix that has two rows the same? Well, it has determinant 0. So in fact, this complicated sum here gives me 0. Okay, huge sum reduces down to 0. What do I have then? This second term here is 0, so the determinant of my row-operated matrix is equal to the determinant of my original matrix. Okay, the two determinants are equal. All right. So final thing I have to do to complete my so that's written here. So final thing I need to do to complete my discussion is what is the determinant of this elementary matrix? Well, you can actually do the same argument on this elementary matrix that you did on the matrix M, because you can just do the very same thing in the determinant expression and find out the determinant of this elementary matrix is equal to 1. So I still have this this relation that the determinant of the product of this elementary matrix times M is equal to the determinant of this matrix times the determinant of M. Okay, so I can just write that here. I can write this as the, let's see if this is going to work, determinant. I guess it's not going to work. Let me write on my OneNote pad. I can write the determinant of the elementary operated matrix here, SG, like this, times M, is equal to the determinant of Sji mu times the determinant of M. Okay. Now this determinant is actually equal to 1, and this determinant is actually equal to this one. So this equation does in fact hold. All right. So we're setting ourselves up for some for the discussion in the next video.